Okay, springs. Springs are one of my favorite things, and just take the time to try and get used to them. So I've just put a spring, I've put a mass on it. By year 13 we'll make that mass jump up and down, and we'll be able to do all sorts of calculations with its displacement, velocity and acceleration, which gets quite complicated. And there's a few things we need to know about a spring. One is very important, K. It's called the spring constant. It's the indication of how much force is required to stretch the spring. A big K means more force required to stretch at a certain distance. So F equals Kx with a negative is our normal formula. And what it's saying is that the force in a spring is, and this is when you stretch it, so you go to stretch your spring, the force, so if I'm stretching my spring down this way, the spring's going to produce a force back that way. That's why we've got a negative. So the force here is for the force in the spring, not the force you are applying to it. It's the force in the spring. The spring constant is a positive number, so x is the displacement. How far did you stretch your spring? So if I've got a spring, I'll do it long here now. That starts off there, no stretch. If I stretch it that far, that's x. The force is back that way. And so K will give you an idea of how much you can stretch your spring for a given force. So K equals F over X. So K is newtons per meter, right? So to stretch it 1 meter, if you need a bigger force, then you've got a bigger K. So you stretch it less. So this brings in some interesting things. If you halve the length of your spring, for the same force, it's only going to stretch half as far. So the K is actually going to change. The K does depend on the length. Right? So if I put a certain force in, maybe 100 newtons, and it stretches 5 centimeters, then I've got a certain K, right? But if I chop that spring in half, the 5 centimeters would have only stretched it half as far, all right? So is the K going to get bigger? Well, if this number gets smaller, then for the same force, the K does get bigger. You've got to put in twice the force. So if you put 2 springs together, all right, so if you put 2 springs together in parallel, that will also double the K, because you're going to have to put double the force to get the same extension. So if you cut a spring in half, you get double the K. If you double the spring's length, you get half the K. These are tricky little things to think about. All right, so what else can we do with springs? We can certainly use them for stretching on things. The other things, though, to remember, a stiffer spring, bigger spring constant. What we want to look at, and one of the main things we do like to look at, is the energy in springs. Now, we all know that energy is equal to force times distance, or we should. We're going to be looking a bit more at energy in the next unit of physics or mechanics. So, force times distance equals energy. So when I stretch a spring, I'll give you another drawing, and I stretch it x distance, and the spring has this constant of that, then the force has changed the whole way that I've stretched it. At first the force was 0. As soon as I started to stretch, I had a little bit of force. So the actual energy is not going to be that simple. If I look at it from this point of view, and if this is my x and this is my force, then I think we know that the actual force changes, right, as the displacement. We just had a look there and we saw that K equals F over X, all right? So as your X increases, your force needed, or your force pulling back against it, increases. And it's a linear relationship because K is a constant. So that means that the gradient here is equal to K. All right? And as we stretch a spring, we want to know, again, the force times the distance. Now this is the force, and this is the distance. So the area under this graph must be the energy. The area equals the energy. Now, the force is changing the whole way, but we know a formula for the force. The force is equal to Kx. So we can actually write that little graph like this. We know the gradient's K, we know the force is Kx, and we know the displacement is x. So the energy is Kx times x, right? If you've gone out to, you've stretched the spring this far, x, and this is equal to Kx. Alright, so the actual energy is going to be equal to Kx squared, Kx being this point here, x being this point here, but we only want half of it, so we divide by 2. So the energy to stretch a spring is equal to half Kx squared. Right? So a little bit on springs there. Watch that video a couple of times. Those things are a little bit tricky.